Now, if the previous example of the length of a circle was trivial, this second example is fascinating. Let me read it to you. Determine the length of the spiral given in polar coordinates as rho equals the exponential of minus phi over 4, with phi going between 0 and infinity. So luckily, when phi goes to infinity, this goes to minus infinity, so the exponential of minus infinity is 0, okay? So this is a decreasing exponential, which is gradually going to 0. So how does this curve look like? This is polar coordinates, so the radius decreases when we increase the angle. It decreases exponentially. So this is how this spiral looks like. Looks like a snail, right? So this is an infinite curve which starts winding around and around the origin, and it never stops going around the origin, but it always gets closer and closer to 0. So now the equation is, does this have a length, and can we calculate it? Is the length infinite, or is the length finite? It's kind of very counterintuitive, right? Because you go around the origin an infinite number of times, and yet you will see that we get a finite answer. So let's see how to do that. So we want to calculate the length. Therefore, we want to do the integral along the curve of dl. So we have to follow all of the steps. Step 1, parameterize the surface. Not the surface, sorry, parameterize the curve. So this is already parameterized. We can just use polar coordinates, okay? Use polar coordinates, but substitute that rho equals the exponential of minus phi divided by 4. Okay, so we can do that. So if you go to the famous table that I provide in the exam, you have cylindrical coordinates, which include polar, right? Just ignore the last equation. So you have the equations for x and y for polar coordinates. So we just use these two values for x and y, but substituting rho equals the exponential of minus phi over 4. So our vector r as a function of the parameter phi is going to be equal to x as a function of phi and y as a function of phi, which we will write as rho cosine phi and rho sine phi, but we are going to substitute rho as a function of phi. Yeah, we're going to do this substitution here. So we get this parameterization, which is exponential of minus phi over 4 times cosine of phi and the exponential of minus phi over 4 times the sine of phi. Okay? By writing this equation into Mathematica, I was able to plot this nice spiral. Okay. The next step is to find dl. Now, geometrical intuition will not work very well, unfortunately. And we will not be able to look this up on any table, because tables are usually for circles, straight lines, and so on. So we are going to use the recipe. And the recipe is telling us that dl is the norm of dr with respect to the parameter times the differential of the parameter. Okay, so we are going to use this recipe. So the first thing we need to do is to calculate the derivative of r with respect to the parameter. So let's do that. dr with respect to phi. So we need to calculate the derivative of this. Since this is a function of phi multiplying another function of phi, we are going to have to use the product rule. So it will be the derivative of this times this without derivative plus this without derivative times the derivative of this. Okay? So you do that and you get for the first component that this is equal to minus 1/4 e to the minus phi over 4 cosine phi, and then plus the minus sign, so minus e to the minus 5/4 times the sine of phi. Okay, so that's the derivative of the first term. Next, the derivative of the second term. So similarly using the product rule, we find Okay? We can take the exponential outside. I think it will make things a bit easier later. So this is our vector dr over d phi. Remember, this is a vector that if you substitute values of phi, it will give you the tangent to the curve. So for different values of phi, you will get the tangent, okay? And the length of the vector will also start getting smaller and smaller because when you increase the parameter phi, the length that you go over is getting smaller and smaller, okay? So this is all contained in the derivative of r with respect to phi, which is that tangent vector here. Now we need to calculate the norm of that. Remember, we have the norm sign there. Yeah, we need to calculate the length of this vector. So we need to calculate norm of this, which means that we need to do the square root of the squared sum of the components. Okay. So fortunately, this scaling factor of the vector is always positive because it's a decreasing exponential. So we can take it outside of the norm. So it won't bother us too much. And now we need to multiply this by the norm of this vector. So we have to do the square root of the two terms squared. And now, as usually happens with these problems, things are going to simplify a lot. Okay, so if you calculate the square of this, you will get sine squared plus this times 2 plus 1/4 squared times cosine squared. Actually, let me write it, why not? So 1/4 squared is 1/16. So that's the first bracket, and then we expand the second bracket. Okay, and now we are very lucky because these two terms cancel out, and therefore we end up with sine squared plus cos squared, which will be equal to 1, plus 1/16 of cos squared plus 1/16 of, sorry, this was sine squared, because it was this term squared, yeah? So 1/16 of cos squared plus 1/16 of sine squared, that is simply 1/16, and the square root of that. So this is basically the square root of 17/16, which is equal to, the square root of 16 is 4, so we get 1/4 e to the minus phi over 4 times the square root of 17. Okay? So this is the norm of dr over d phi. So finally we can find dl. We just need to multiply that norm by d phi. So dl is equal to 1/4 e to the minus phi over 4 square root of 17 times d phi. That's dl. Okay? So step 3, evaluate the integrand. So it's just dl. That's the only integrand we have. We don't have a function there. We just have dl. And dl is already written only in terms of the parameter phi and using constants. So everything is ready. So step 4 is calculate the integral. So let's do it. So the length of this infinite spiral, we are about to find that it's not actually infinite, even though it goes around the origin an infinite number of times, and yet it's finite. This is one of those magic moments of maths. So the length is the integral over the curve of dl. So we substitute dl. It's 1/4 square root of 17 e to the minus phi over 4 d phi. And what are the limits for phi? So phi is going between 0 and infinity. So between 0 and infinity. Okay, so this is all a constant. It can go outside. And then we are just left with the integral of the exponential of minus phi over 4. So the answer to that is very easy. It's simply 4 times the exponential of minus phi over 4. Sorry, minus 4 times. Yeah? Because if you do the derivative of this, you get minus 1/4 multiplying here, which cancels out with the minus 4. So you end up with the exponential only. So this is the integral that we are looking for, evaluated between phi equals 0 and phi equals infinity. So this gives you square root of 17 over 4 times, when you evaluate this at infinity, you get the exponential of minus infinity, which is 0. So you get 0, and then minus 4 times the exponential of minus 0, and the exponential of minus 0 is 1. So you get 0 minus minus 4, which is 4, which cancels out with the 4 below. So you end up with square root of 17. Amazing. So you have this spiral, which is going around the origin an infinite number of times, and yet the length of this spiral is the square root of 17. Why not? Amazing, right? I hope you liked it. And here you can very clearly see the steps needed to calculate dl. Okay? Thanks for watching. See you in the next video.